Go on.
Okay, thank you. President Roosevelt said to Senator McKellar, I need to hide a large amount of money. I got to put a large amount of money against the war effort, and I can't let the press or anyone know how much it is or what it's being used for. Can you help me with that? Senator McKellar said, yes, Mr. President, I can do that for you. Just where in Tennessee are you going to put that thing? Now, that might have had more to do with us getting selected in East Tennessee than any ridges and valleys, lay of the land, or even proximity to the Norris Dam, which was the first dam created by the Tennessee Valley Authority. Now, Elizabeth, you tell them a little bit about this map and also about the aerial view that we're going to show next.
Thank you so much. Basically, I'd like to completely express and echo his comment on the fact that there were political considerations in choosing Oak Ridge. And one similarity to that is I came to Oak Ridge from the Paducah Gaseous Diffusion Plant. And coincidentally, that was constructed in 1952 in Kentucky. And Kentucky was the home state of the vice president of Harry S. Truman. So there were some very similar reasons as to why, Kentucky was chosen for the gaseous diffusion plant and Tennessee for the Manhattan Project. Right. Now, the other part of it is anytime you have a human endeavor, there's always politics and interpersonal relationships involved, but there's also the technical reasons that an area is selected or that something will work. And what's unique about East Tennessee is that in this area, just within the decades before, there had been a huge endeavor initiated with the Tennessee Valley Authority and all of the dams constructed. So you had a huge volume of water that was readily accessible for these processes. You also had a continuous, constant source of a large volume of electricity, that could be used for this effort. Some other things that they were looking for is something central to the country that would be immune to enemy-based carrier ships and possible attacks from that. They wanted secrecy and efficiency in a site that was large enough for all of the processes. They needed a climate suitable for winter construction, a large labor pool, transportation accessible. And if you could go back to the original aerial photo for us, please. And also you can see it on here a little bit, but here it is so well depicted. The unique thing about Oak Ridge, Eastern Tennessee, is that you have these extremely tall ridges, that go up about 150 feet above the baseline where the valley is. And what this allowed was a natural barrier for explosion. And so you can see from where Oak Ridge National Lab, and if you'll point for me, Ray, you can see Oak Ridge National Lab is separated from Y-12, by a huge ridge line. And then if you go very far to the left, there is a very, very distinct ridge line. That's actually SNS at the top of the hill, but keep going up about an inch. That ridge line separates Y-12 from the city. So you could have all of these installations in very, very close proximity, but they were still protected from an explosive impact. And so, moving on, the other thing I want to mention, setting it back up again for Ray, is, the basic military objective of this entire mission, the main problem of the Manhattan Project was to produce enough fissionable material in a large enough quantity that was pure enough to be able to build the bombs. And the really, really fascinating thing that I find about this whole endeavor is that when they started, they didn't know which way would work best. And there were actually 4 or 5 different discrete technologies that they could use. The 4 that they were looking at initially, and I'm looking at my notes, I've not done this as much as Ray has through the years, so he knows it all by heart. That there was the electromagnetic process, the gaseous diffusion, liquid thermal diffusion, and gas centrifuge. Of those 4 processes for uranium-235 enrichment, they selected to do all of them except for gas centrifuge initially. And then also ORNL was the construction, the location for the pile, which was for plutonium. So with that, if we'll go ahead and go back to you, Ray. Thank you.
All right, my pointer is pointing at the graphite reactor. We'll see another image of it later that'll show you in more detail, but it is still there today. It's a on the National Register as a National Historical Landmark and is a part of the Manhattan Project National Historical Park. So that's a significance of there is that it was the first full-size uranium reactor that proved you could produce plutonium. And then Y12 up here across Chestnut Ridge and between Pine Ridge and Chestnut Ridge in Bear Creek Valley is where the electromagnetic separation plant was. And that's where the nuclear weapons plant, Y12 National Security Complex, is today. And Elizabeth also mentioned the spallation neutron source, which is up here on top of Chestnut Ridge, is the most powerful pulse neutron source in the world. And again, that's a part of the National Laboratory. Now, let's go back in history and think about 1945. By August of 1945, this area that was once small communities with about 3,000 people living here on 1,000 farms, by August, it was the 5th largest city in the state of Tennessee. Wasn't on any map, had gates on all of the 7 roads leading into it. Those gates stayed there until 1949, when the main gates were opened and the public could come into the city for the first time. At that time, they established gates for the 3 local government sites, Y12, the Oak Ridge National Laboratory by then, and the K-25 gaseous diffusion plant. Let me quickly point out one area. My pointer is pointing toward the guest house, which was a hotel where people stayed. And that's where the most famous picture of Robert Oppenheimer was made, was right by the fireplace in that guest house. It's today a senior living center, and I have reproduced that photograph and put it on the mantle that's in the picture that was made in 1946. That's the Chapel on the Hill, a very picturesque little church. This is the administration building, which is where the federal office building is today. And the area here is the Jackson Square area, which was the commercial area for the original town site for the original Oak Ridge area during the Manhattan Project. This gives you a little better view of the Jackson Square. By the way, these buildings are still there today. These dormitories are all gone, however, but the Jackson Square itself remains just like it looked in 1945. The buildings have been maintained. And of course, there are different stores in it now. We put a fountain out in the middle of the parking lot, but it's still recognizable as the original Jackson Square. This is what Y12 looked like in 1945. These large buildings, there are 9 of these buildings, and they're all still there today, but they are going to be demolished, many of them over the next few years. However, this particular building right here, this one is Beta 3, 9204-3. It still has 2 sets of the beta calutrons, the second stage, and I'll show you the calutron in just a minute. This stands for California University Cyclotron. But that particular building, and also this building right here, this is building 9731, and it has the only existing alpha calutron magnets in the world. And that building, 9731, and building 9204-3, we call it Beta 3. Those 2 buildings are also a part of the Manhattan Project National Historical Park. Ernest Lawrence is the one that invented the calutrons, and he named them after the California University cyclotrons, so he calls them calutrons. Now notice it's in an oval shape, and that's why they called them a racetrack. But the separation of the uranium took place between these two magnets and the pairs of magnets. There have been 96 calutrons here. This particular vacuum chamber, these chambers you see here, would be inserted between two magnets. And there, again, there'd be 96 of them here. Now, I'm going to show you something real quick. If you look at my picture, if I took two rubber bands and held them down from my hand, put a golf ball on one and a ping pong ball on the other, and then I spun them real quick for a half a turn, that golf ball would stretch that rubber band further than the ping pong ball. So I'd get two arcs. The same thing happens with uranium-235 and 238. There's 3 neutrons difference. And when you put them in between those magnets, one ion at a time, centrifugal force will make that 238 bend. The magnets cause it to bend. Centrifugal force will make it bend a slightly larger arc than the 235. So you can catch the 235 up at the top. That's a simple physics process that works like it is a mass spectrometer, and it will separate not just uranium, any element that you run through those magnets with the proper setting on the magnets can be separated into its isotopes by that process. Now, there were a lot of women that were working at Y12, 22,482 workers there in August of 1945. Maybe 100 of them, the chemists, would have known they were working with uranium, but even they wouldn't have known they were making a bomb out of it. Some of the women that were hired were young girls right out of high school, hired to be cubicle operators. Interestingly enough, this one in the right of the picture is Gladys Owens. Gladys worked at Y12 from January till August of 1945. And then she left. She came back. Now, by the way, a good friend of hers had sent her a letter. She lived up in Kentucky and said, Gladys, you need to come to Oak Ridge and get a job. There's men down here. There wasn't any young men up in Kentucky. They were all in the military. But there was a special engineer detachment here in Oak Ridge, so there were young male soldiers here. So Gladys got her a job. But she left when the war was over and they laid off a lot of people. She came back in 2004. She saw this picture of her in the American Museum of Science and Energy, told the director, that's me in that picture. Well, Steve Stowe, the director, called me and said, Ray, we found you a calutron girl. Now, that's where that term came from. We started using it, calling these young ladies calutron girls. I took Gladys out to Y12, set her up on a stool, took her picture, and she said, Ray, I never did know what I was doing when I was working out here. Remember, all those young girls wouldn't have had any idea what they were doing. They were had been trained to keep those meters on a certain spot. And she said, can you show me what I was doing? I said, yeah, Gladys, I can show you. So I opened up one of the cabinets. I said, Gladys, when you were adjusting those knobs, you were changing the value of a rheostat down here. She reached over and tapped me on the arm. She said, Ray, I still don't know what I was doing, but I know if I had any bobby pins in my hair, they'd just go stick to the wall somewhere. Largest magnets in the world at the time would pull the hairpins out of the lady's hair when she was there. This is what Y12 looks like today. Down in the lower right is the New Hope Center. And in that New Hope Center is a history center. The Y12 History Center has a model of Little Boy in there, but it also has a lot of other historical information that you can learn about the history of Y12 there. The highly enriched uranium materials facility is right here, just about a half a mile down the road. And just beyond it, just west of it, is the new uranium processing facility, a $6.5 billion construction project that has just been completed, and they'll be operational within another year or so. And then this is the K25 building, the gaseous diffusion building. That was actually a mile long from one end of the U around to the other. It was under 44 acres under one roof, largest building in the world at that time under one roof. Now, it could operate at about 1/10 the cost of Y12. Remember, Y12 was a batch process, but the gaseous diffusion process was a continuous operation, about 3,000 stages that it would run through. And the way a gaseous diffusion worked is there's a barrier, and you think about a space the size of my thumbnail, there'd be 1,000,000 holes, all the same size, all equally shaped, and that 235 being just a little lighter than the 238 would go through those holes a little faster, a little easier than the 238. So if you did that 3,000 times around this U, you would begin to accumulate a larger percentage of uranium-235. By December of 1946, they were able to produce weapons-grade uranium in the K-25 process. So that meant they didn't need the calutrons at Y-12 anymore. They shut them down, had a lot of buildings left. Jack Case went out to Los Alamos and brought back the technology for converting the powdered uranium that had been sent out there into metal and making the uranium parts. And for the thermonuclear bombs, all of the secondary parts are made at Y-12 for all of the nation's nuclear weapons. And as they're being dismantled, they're coming back to Y-12, the secondary, and being separated out, the uranium put in the highly enriched uranium materials facility, and the lithium and tritium and those things coming out as well. Now, this is the S-50 plant, the thermal diffusion plant. This is the one that Robert Oppenheimer told General Groves, you got that steam plant, biggest steam plant in the world, but the barrier is not ready for the gaseous diffusion yet. So why don't we build a thermal diffusion plant there? He knew the Navy was experimenting with it. So Groves went to the contractor and he said, I need a thermal diffusion plant built. I need it built right by that steam plant, and I need it in 90 days. The contractor said, that's impossible. It can't be done. Groves looked him in the eye and said, you've got 80 days. They built it in 76 days, operated it about 3 months, and it's calculated that it shortened the war by about 3 weeks. Now, during the construction of the K-25 and the S-50 plant, 15,000 people lived as construction workers in an area across the road from K-25 called Happy Valley. This is the gaseous, or the graphite reactor that I told you about earlier. I'm going to show you an internal picture of it. That's what the face of the reactor looked like. And again, it's the first reactor built that proved you could produce plutonium from uranium-238. It used natural uranium. And then they went out to Hanford and they built 3 more reactors on the Hanford, Washington, and built 3 more reactors on the Columbia River. And that's where the plutonium came from for the gadget for Fat Man and for the nuclear weapons that we have today. Now, this is the Oak Ridge National Laboratory, and I'm going to turn it back over to Elizabeth and let her tell you something more about the Oak Ridge National Laboratory, its history and today. Elizabeth?
Thank you very much. We appreciate the opportunity to discuss this today. It's such a fascinating topic, the Manhattan Project. One of the most amazing human accomplishments in the history of the world, in the time frame that they completed it and the number of scientific minds that were brought together. Oak Ridge National Laboratory, we have 6,000 employees that work here at the lab. We have one of the most diverse energy portfolios in the complex, the largest materials research portfolio, the world's most intense neutron source, multiple scientific computing facilities, a world-class research reactor in Haifa, while we host over 3,000 guest researchers every single year. We just finished celebrating our 80th anniversary here at the laboratory, and we very much look forward to another 80 years in front of us. So thank you for this opportunity to talk about the history of Oak Ridge.
Yes, and thank you for letting me talk about our history somewhat and to share some stories with you.
Elizabeth and Ray, thank you so much. What a phenomenal insight into that amazing story of Oak Ridge. Every time I listen to you, including what the oral histories you have on the website, Y12 and Oak Ridge websites that are in our history link on INMM.org, I learned something new every time. There was one question that popped up and that is, are calutrons still used today to separate isotopes?
And that's a good question, and they are used over at the Oak Ridge National Laboratory as electromagnetic separation units. I kidded them and told them they ought to call them calutrons, and they laughed at me and said, "No, Ray, we're not going to call them calutrons," and that's okay. But yes, the Oak Ridge National Laboratory has operating electromagnetic separation units today, and it's actually a growing business for them. Now, let me say that the calutrons in Y12, operated by the Oak Ridge National Laboratory, did operate up until 1998, and they were shut down at that time. Those are the ones that are still remaining in Beta 3, Building 9204-3, and we hope to keep those for display for people to see the original calutrons. Elizabeth, would you want to add anything to that? Okay.
You covered it well. Thank you.
You bet.
Okay, thank you very much. And for those of you that have seen the Oppenheimer movie, you may recall they had two fish bowls. I don't know if they actually had that in real life or not, where they put marbles representing the amount of material U-235 from Y12 and plutonium from Hanford to show that they needed to fill those in order to have enough to make the weapons. But those are the marbles that we just heard about from Y12. I apologize to everybody. Just as I unmuted to give the introduction, my whole computer froze and I had to reboot everything and get back online. I appreciate Tina doing the introduction for me, and I appreciate all of our historians today giving us this information. And hopefully all of you that are listening, if you have other links or information that might be useful to put on our INMM history website, please send them to me or to INMM headquarters, and we'll make sure we include those on our history webpage. Right now, I'd like to introduce Dr. Robert Franklin from the Washington State University, who is in charge of the history project out there for the Hanford and the Tri-Cities area. Dr. Franklin?
Hi, welcome, or thank you. Could somebody enable my video?
Everyone should be enabled.
The host has stopped my video.
Oh, sorry about that. Yeah, I turned you off while the others were speaking. Bear with me.
Sure, no problem.
I do like your hibiscus flower, however.
Thank you. Reminds me of Hawaii. Okay, well, while we're waiting for that, it's not, no one has to see my mug.
Go ahead.
Okay, sweet. We're getting there. All right. Hi, thank you so much for having me. I'm going to talk to you about the Hanford site and, of course, its role in the Manhattan Project and in just a little bit in the Cold War, or at least, its history. So the Hanford site itself, and let me get my pointer option. There we go. The Hanford site itself covers 586 square miles, the original site. This is a map of the boundaries of the site. What is in the kind of checkered there is the original boundary of the site, the land that was taken by a declaration of taking in December of 1942. And the modern border of the site now is kind of the beige area. The greener outer edges have been returned to either public use or management by a different agency. Fish and Wildlife manages part of the Arid Lands Ecology Reserve. And of course, this section of the Columbia River that flows through the site, one of the main reasons the site is here is is the Hanford Reach National Monument. This is an undammed section of the Columbia River, the only free-flowing section of the river in non-tidal free-flowing section of the river in the United States. So a very valuable habitat for salmon, sport fishing, recreation. The site itself was chosen for several factors. Groves had sent Lieutenant Colonel Franklin Matthias out west to scout sites. He scouted, I believe, 7, And Hanford was actually the last. And when he flew over the site on December 22nd, 1942, he saw exactly what he was looking for. He saw the Columbia River, a free-flowing, fast-flowing, relatively clean, cool river that flowed year-round. He saw a rural area in this 586 square miles. There were only about 1,400 settler residents and several hundred indigenous occupants who used the area seasonally, had been using the area seasonally, of course, for many thousands of years. And the Hanford site is also home to many important indigenous sites for some of our area tribes. He also saw lots of kind of fine sandy soils that would be good for construction of these large concrete buildings here. The basalt, thousands of feet of basalt underneath those sandy soils that would provide firm foundations, and plenty of electricity coming through the area thanks to the Grand Coulee and Bonneville dams. Of course, this area had been used, like Oak Ridge had a population in the area long before the Hanford site came. The area for many thousands of years has been home to tribes such as federally recognized tribes such as the Yakima, the Wanapum, the Yakima, the Confederate tribes of the Umatilla, the Colville, the Walla Walla, Cayuse, and the Nez Perce tribes, all federally recognized tribes. And one unfederally recognized tribe, the Wanapum people, had lived within the area and just north of the Hanford site seasonally for thousands, from time immemorial. And Wanapum in Sahaptin, which is the lingua franca of the mid-Columbia region, translates to people of the river, meaning these are the people of the Columbia River. The area saw relatively late settlement for the Western United States. We're not technically a desert, but we just get a little too much rain to be a desert. But you do need irrigation to farm the land here. And this area was not really settled with agriculturalists until the beginning of the 20th century, is when you saw settlement projects like the one here, for White Bluffs and the town of Hanford. White Bluffs is founded a bit earlier in the 1860s because it's an important overland route, but it's a very, very small town until the 1890s, 1900s, when it balloons up to a town of several hundred. Hanford is founded in 1908, also just a town of several hundred. And then the town of Richland has about 247 residents in 1940. So all of the permanent residents were their land was surveyed by the government. They were given what's called this survey here. You can see this on the left side of my screen, that kind of tallied up their land and buildings, and they were given this money and forced off the site to make way for the Hanford project. So as Ray had mentioned, the Hanford site made plutonium for the gadget, and then the bomb. Fat Man dropped over Nagasaki, Japan, killing about 80,000 Japanese in total, and then the majority of the United States plutonium for during the Cold War. The journey really kind of starts in the 300 area. This was a research and fuel cladding area where natural uranium was brought in and turned into fuel by jacketing billets of it. So kind of think of like a soup can-ish size, a little thinner and longer than that, but think of, kind of like a can off the shelf, or like a Red Bull can, jacketed in aluminum, and then that was trucked up to the three reactors, the B, the D, and the F, that were built in the Manhattan Project. And these reactors loaded in that fuel and then the fuel underwent transmutation within the reactor, moderated by graphite, to produce small amounts of plutonium. The amount of aluminum uranium that could turn into plutonium was a very small amount of the natural uranium, about 0.8%. But of course, each reactor had 2004 process tubes. Each one of those tubes held 32 slugs of uranium. So we're talking a massive amount of metal, and all of that produced a massive amount of heat. These reactors used hundreds of gallons of water per second to cool them. And that water would come in at an ambient temperature of about 60 degrees, and it would leave the reactor about a second later, close to boiling, just shy of boiling. And then once it had cooled some, would be deposited back into the river. While a lot of the Manhattan Project story is one of physics, especially what's happening at Los Alamos and also at Oak Ridge, what's happening at Hanford is kind of less a story of physics than it is a story of engineering. And really the role of a company like DuPont and taking the reactor designs from the physicists at the MET lab, the metallurgical lab, and making very important changes to them to making them functional and reliable. But even kind of simpler than that, the story of Hanford is really much more akin to the story of mining and smelting. We can think of some way of the reactor as producing an ore that we want. It's taking in mined uranium, but it's creating the conditions to produce a different type of ore. But that ore, that plutonium, is still has to be smelted out of these irradiated fuel elements. That's where the plutonium separations buildings come into play. These long canyons called Queen Mary's, they were about 60 feet tall, but 800 feet long. A good chunk of the building is actually underground in these shots, so it doesn't quite look 60 feet tall, but it is if you go from the basement of the building. These canyons would take those irradiated fuel elements and then through a series of batch process chemistry would isolate out the plutonium, and of course treating the rest of the material, the vast majority, 99+% of the rest of the slug, initially as waste product. And this is of course where one of the things Hanford is most known for is its massive amounts of nuclear waste. 56 million gallons of waste produced during the Manhattan Project and the Cold War. This process was later refined. We were beginning in the Cold War, we started extracting the uranium and the plutonium and reusing the uranium, but initially on, everything was a waste product. We were just trying to smelt out that plutonium. And in that way, what's happening at Hanford is really much more akin to a smelting operation, and the waste produced is much more akin to the waste in the mining and the smelting operation. And so this really kind of connects Hanford with a larger story of kind of mining and environmental impact around the United States than other sites of the Manhattan Project. This is the inside of one of these canyons. Over here on the right would be where the cells, there'd be 40 plus cells where this batch process chemistry, this plutonium extraction would happen. And on the that's on the right here where these people are standing. On the left would be the operator's gallery. This is where people would actually run this process, where they would pull samples from, they would introduce catalyst. They use these large Toledo scales to actually weigh out large amounts of catalyst to add at different stages. And this was separated from what's happening in the gallery, is separated from what's happening in the canyon by several feet of concrete, because what's happening in this canyon is so incredibly radioactive and toxic that was needed to protect people in this operating gallery. And if you kind of take a look at how this building is laid out, with its kind of long series of processes, it really is. And here's another shot of that canyon, and it's, this kind of, again, this long batch chemistry process, all operated completely remotely by an operator using a crane to lift up some of these sarcophagus lids to install or do maintenance on equipment there. There would be no one in this when it was running, because even these giant concrete sarcophagi were not enough to protect people in the gallery when there is processing work going on in here. Really fantastically dangerous places. They're really kind of laid out similarly to ways that modern smelting is laid out. Again, kind of furthering this comparison point between what's happening here. It's really less physics and kind of more engineering and industrial work is happening at Hanford, even in the way that these things are operated by crane. It's kind of something that struck me. It's hydro engineering, really, is a lot of what's happening here. These are shots of the single-shelled waste tanks, where this waste, high-level waste from this process, was located into. Initially, they built single-shell tanks. Later on, they built double-shell tanks. There's 177 of these tanks in total, holding that 56 million gallons of high-level waste. Low-level waste was just routinely discharged into the ground. First, just on the ground, and then later in cribs through the 1980s. So here, Jack Rhodes, someone that we interviewed, talks about Hanford safety standards, and I've enabled my video, so hopefully this will play for you.
When they built the nuclear industry, they did not have safety standards for the nuclear industry because it was a brand new industry, okay? So if you looked at the operation of the uranium side, why then they used the safety standards of a steel mill and a blast furnace to do the safety standards for like phenol and these other uranium enrichment places. And if you looked at the chemical processing in the canyons, they looked to the petroleum cracking industry for safety standards. And if you look to the waste disposal, which was the operation of the tank farms and the barrel grounds, it had the same basic safety standards and interest as a commercial landfill.
So during the war, the town of Richland is the pre-existing town, the small town of 247, is taken for the site, but it is, unlike Hanford and White Bluffs, which are the two towns on the Hanford site, Richland is transformed into some kind of an atomic post-war suburban utopia, in that it is a town where everyone works for the contractor, first DuPont and then General Electric. It's a town where people are provided government housing, and it is, but unlike Oak Ridge, Los Alamos, it is not a secret town. It doesn't appear on a lot of maps, but it's also not guarded. People are free. Outsiders are free to come in and leave Richland. I like to say, think of it, it's a kind of a secretive city, but it's not a secret city. But certainly it was not a well-known city, and one would really only come to Richland to do Hanford business. This is a shot of kind of modern Richland. Some of this is still here. The center, the parkway here is still a recreational area for people. The Uptown Mall is just getting constructed, kind of in the upper left of this building. This kind of V-shaped building is now today the Holiday Inn, but there's still a hotel on that site. It used to be called the Desert Inn. So much of Richland has certainly grown over the years. In 1950, when this photo is taken, Richland's about 18,000 people. It's today about 65,000. So certainly grown, but in this period, really a suburban utopia, oriented around the car and, of course, everyone's work at Hanford. And part of this utopia, of course, was the provision of high quality housing for workers. DuPont, the company that ran the site during the Manhattan Project, insisted that workers be provided some sort of housing that was not barracks. The Army Corps Groves said, well, the Army builds barracks, and DuPont said, well, our people aren't going to live in barracks. And so they kind of compromised and built these kind of minimalist traditional alphabet houses, named because each of the plans had a different letter of the alphabet. This is an H here, and these were solid kind of Douglas fir construction, and many of them are still here today. Some changes, obviously. There's a lot more landscaping. The trees are a lot taller, but many of these houses are still here today, still being lived in. And really, I love this picture here because it really reinforces the white picket. Right here, we have the white picket. We can see this kind of burgeoning utopia where people are going to work, but that work is secret, and people are kind of trying to build their lives in this secretive city. Now, for folks that lived in Richland and were gainfully employed by the Manhattan Project, this was a time that people I've interviewed remember incredibly fondly. Growing up, no one locked their doors, no one knew what their dads did, but they had all that they needed. On the other side of that, Hanford is also a tool or a place of segregation and loss for others. And so, of course, for the indigenous peoples of the area, the Wanapum, the Nez Perce, Yakima, and others, Hanford represented a permanent, or at least a semi-permanent barrier for them accessing many important cultural, traditional sites, parts of their religion, what are called today traditional cultural properties, because not only was there a security fence, but some areas of the site are too contaminated to allow people to visit. And so this is a picture of Johnny Tawamuash and Pakayatu, two Wanapum elders, standing before the Yakima barricade, and really kind of showing that enforced displacement of their people. In addition, Hanford was a segregated space. The army was segregated at this time. Washington did not have any laws mandating segregation, but DuPont and the military chose to segregate all facilities at Hanford. Work was segregated, living was segregated, even as you can see here, entertainment was segregated. And so as Joe Johnson said, a gentleman that we interviewed many years ago, blacks live with the blacks, whites live with the whites. And for those that could not find housing in Richland, they had to live in East Pasco. And the east side of Pasco is one of the three cities of the Tri-Cities. The east side of Pasco was a place where people lived in dangerous slum-like conditions, as you can see here on the left. This picture taken in 1948. East Pasco was a part of town that was on the other side of railroad tracks, the largest rail hub west of the Mississippi. So really segregated from the rest of Pasco, the white part of the Tri-Cities. And it was a place where people lived in dilapidated trailers, automobile trailers, camped in tents. They had no running water in their houses. Many people did not have electricity. They did not have sewer systems. They did not have streetlights. They did not have paved streets. It was, all intents and purposes, a ghetto was created for Black workers. And this persisted up through to the civil rights era, where there were many important civil rights protests in Pasco that mirrored larger protests nationwide in both the North and South. But of course, other elements of race in American history are present at Hanford, including, of course, blackface entertainment was quite popular. Many programs from the 1940s in Washington showing black-faced performers. Here I have just a very short clip from James Pruitt. James Pruitt moved up here in the late Manhattan Project to work in the Tri-Cities, and here he talks about how he experienced moving from the Tri-Cities from Mississippi.
And I was working in Los Angeles, and he asked me if I wanted to make some money to come up to Richland, Washington. Mm-hmm. So I decided to come up here, and I stayed up here for 6 months. And the dust and the tumbleweeds were so bad, I went back to Los Angeles and stayed 3 months. Okay. And I came back, and I've been here ever since.
Okay. Jim, let's talk about the social environment in the Tri-City area. Again, Pasco, Kennewick, and Richland for the African American. at that time, 1948. What was the relationship between the African American and the, we'll say, the white community or majority community at that time?
Bad. Very prejudiced, very racist. And I was surprised when I came here to find a place that I had left a few years back from Mississippi, and came here and found the same thing that I found in Mississippi.
Of course, Hanford was incredibly proud of its ending, its role in ending the war. Here are, of course, two from August 6th and August 14th about peace. Notice that the importance Richland was placed on our bomb doing the job, but also in this peace newspaper on the left. Notice what's the second most important headline here is that our plant will not close, thereby reassuring people in the at Hanford that they would have jobs for many years to come, of course, to build a lot of the plutonium for the U.S. nuclear weapons arsenal. And with that, I'll leave you with my favorite ending slide, this picture of this wonderful plutonium pig.
Dr. Franklin, thank you so much. What an incredible story there, paralleled with a timeline of society in the United States as well. I look forward to seeing a lot more information from your history website and stories like this. Thank you very much.
You're welcome. Thank you.
Let's move on now to Rebecca Ulrich from Sandia National Laboratories to talk about how they moved the engineering effort from Los Alamos down to Kirtland Air Force Base. Rebecca? You're still on mute there, Rebecca.
Maybe, Jack, we move to Tom Ramos and then we'll come back to Rebecca.
Okay, she may have encountered something similar to what I
Yeah.
did. Tom, do you want to pick up on the Livermore story?
Sure, thank you, Jack. My camera looks like the camera is still shut off, but I guess what I'd like to do, I'd like to follow on these great histories we just received from Tennessee and Washington a little bit, and let me give you a little background on how those plants, why those plants were built, and what that's about. Okay, so, and I'll have to talk quickly, of course, to get through it all. But nuclear fission, it was discovered after an experiment by a physicist named Enrico Fermi in Rome. He saw some anomalies with uranium, and that led a chemist in Berlin, Germany, to repeat Fermi's experiments. He did the experiment, he saw some anomalies going on, he couldn't understand it. And he wrote a letter to his person he worked with for years, a woman, Jewish descent, Lisa Meitner, who had left Germany because of the anti-Semitic laws that were going on with the Third Reich, the birth of the Third Reich, and she was living in a village called Kungälv, Sweden. And amazingly, within about a week, Lisa Meitner was able to come up with a theory of nuclear fission, along with her nephew Otto Frisch. And she and her nephew published the article in the Nature magazine, the physics magazine of Great Britain, announcing it. And one of the things they announced is this new reaction, or this new form of energy, is 1,000,000 times more energetic than the energy you would get from a chemical reaction like with TNT or something. And that caught the imagination of physicists very quickly. And also, amazingly, within about 6 months, Niels Bohr, the great Danish father of the atom physicist, and John Wheeler, one of the greatest American physicists of the 20th century, they got together, wrote a paper at Princeton, and in which they said, well, what's really happening is the fissioning is not occurring in the more prominent uranium-238, but in the uranium-235, which represents 0.7% of natural uranium. And the implications were clear that if you wanted to make a bomb out of these things, you had to make a critical mass of the uranium-235, which was the fissioning element of uranium. What they used, by the way, was a statistical physics that also Enrico Fermi had built up about 10 years earlier, and they came up with their arguments. Anyway, there was a physicist named Ernest Delano Lawrence, who's running the University of California Radiation Laboratory in Berkeley. He read it and he saw the immediate implications of that. Then he saw that it's possible with this new form of energy that one could form a bomb 1,000,000 times more powerful than TNT. And he immediately set about seeing, is it possible, or coming up with a way to separate out the uranium-235. His idea was the Germans had plenty of smart physicists. They knew what they would take to make an atom bomb. And therefore, it was important to get this thing done before Hitler's scientists did. And that's when he came up with this idea of using when he invented the calutron, which we heard. And it worked. At Berkeley at the RAD lab, they used it, and they were able to, on their first initial trials, enrich uranium from 0.7% to 3%. And so it looked like it really would work. He took this idea to Vannevar Bush, who today would be called the President's Science Advisor. Bush saw it, and he wasn't convinced you could make a bomb, even a bomb out of this thing. And I hate to contradict our good friend from Tennessee, but that letter from Einstein to Roosevelt wasn't quite as impressive on Roosevelt as you might think. Ironically, Enrico Fermi gave a briefing earlier about the new force of uranium and how it could lead to a very massive bomb. And that information got to Roosevelt through the Navy several months earlier. In any way, Bush was not certain, but then the British got together, led by a physicist named Mark Oliphant. They wrote a report called the Maud Report, and it went to Washington. Nobody read it in Washington, and Oliphant, in desperation, flew out to Berkeley, met with Lawrence, and explained what was happening, and Lawrence could see the importance of this, and he arranged for Oliphant to meet with Bush back in Washington. And once Bush understood that to make an atomic bomb, all he needed was about 50 pounds of uranium-235, well, that was an engineering task that could be done. He went to President Roosevelt and then got permission to start an atomic program. The next thing Bush did was go to the Chief of Staff of the Army, General Marshall, and General Marshall accepted the challenge of taking on the project of making an atomic bomb. And they used the Syracuse district of the Corps of Engineers for the Army to do this. And there was a Colonel, John Marshall, no relationship to General Marshall, and he was given responsibility for it. And his deputy, Marshall's deputy, was Ken Nichols, the Lieutenant Colonel Ken Nichols, and they began projects on it. Bush, in the meantime, sent out engineering teams, and they knew they would need a lot of electricity for this system that Lawrence had come up with, the electromagnetic system or the calutron system. And so the Tennessee Valley Authority was a natural place to go to. And they found his engineering team recommended a nice area near the Clinch River flat. We've seen it. The locals called it Oak Ridge. And they told Marshall to get started on this. But Colonel Marshall was reluctant to get something started. He wasn't sure there were these competing processes that we heard about. He had gaseous diffusion led by Harold Urey, a Nobel laureate. The centrifuge was run by Jesse Beams, who was a friend of Lawrence's, actually, at Yale University. And then you had Lawrence's electromagnetic process using the calutrons. And Marshall had the expectation, well, let them prove themselves before we purchase this land. Bush could see a catastrophe coming on. Nothing was happening. He went back to General Marshall, said, look, I'm going to be briefing President Roosevelt in 2 weeks, and I'm going to have to report on the lack of progress. General Marshall got the message, and they more or less relieved Colonel Marshall, and they brought in Colonel Dick Groves. And I know you see it in history, it's Colonel and then General Leslie Groves. He hated the name Leslie, so for his benefit, he went by his middle name, Richard. So it's Dick Groves then was called in and was given the mission to start this thing up. And within 72 hours, he purchased Oak Ridge. And within another short while, he would be purchasing and making a contract with DuPont to make plutonium, but I'll get to that later. And then with that, one of the first things to occur was to start the Y-12 plant. Groves' deputy, Ken Nichols, goes down and he needs to create these huge magnets. I think they weighed 30 tons apiece. And copper was a wartime metal that was very rare. So Nichols went back to the West Point silver repository. Nichols was a West Pointer. He knew that there was a silver repository at West Point, and he immediately ordered something on the order of 30 or 40 tons of silver out of there, and they were going to make the wires out of this. So great engineering efforts went on, and Lawrence went in and took charge, and he basically took 100 physicists out of Berkeley that had been developing the Calutron, and they shipped down to Oak Ridge to get the project started. And it was a horrendous project to get that thing going. Now, meantime, back at the University of California laboratory in Berkeley, the RAD lab, as we called it, another physicist by the name of Edward McMillan, he decided he wanted to replicate the experiment in Germany that had discovered nuclear fission. And he did. He was able to use a cyclotron to replicate that. But McMillan, being McMillan, he went in and did much more in-depth analysis of this. And along with a friend of his, a chemist that was working down the hallway at the RAD lab by the name of Glenn Seaborg, the two of them basically got together and they discovered neptunium and then plutonium. These were named after the planet. Uranium is named after the planet Uranus. Neptunium was the next element they discovered, and that was named after Neptune. The next planet out was Pluto, and then they also discovered plutonium. In addition, the Glenn Seaborg also worked, and within the next few months, he came up with a process that Bob Franklin talked about. It's the Purex process. So Seaborg, within the first year of discovering plutonium, actually came up with the chemical engineering process to separate the plutonium from the spent fuel. That was basically to make the plutonium, the uranium-238 absorbed neutrons became uranium-239, and that would decay into neptunium, which then decayed into plutonium. And so after a period of time, you then were accumulating plutonium within your uranium fuel, and then you had to extract the plutonium. And as we heard, he had a great talk about it. And it was like a smelting process using that Purex process to go. Then Dick Groves decided he needed to get a laboratory to consolidate all of these efforts going on within the Manhattan Project. The name changed when they switched from Connecticut and they moved their headquarters to Southern New York in Manhattan. And they changed the name from the DSM project to the Manhattan Project. And Groves flew out to Berkeley and he asked Lawrence to start another laboratory, this time to make the final designs for the atom bomb. And Lawrence told Groves, yeah, he would love to help, but right then he was up to his ears trying to get operations at Y-12 running. By the way, as a small matter, Y-12 is from the coordinates at Oak Ridge. If you look at a map, one coordinate is letters, the other coordinate is numbers. And so Y-12 was at the Y-12 coordinates of the Oak Ridge Reservation. K-25 was another aspect. And Lawrence told Groves he couldn't do it because he was much more needed at Y-12 to get Y-12 up and running. Otherwise, we're not going to have the raw materials to make an atomic bomb. Groves understood that, and Lawrence suggested he talk to his theoretical physicist within the RAD lab, Bob Oppenheimer. And Groves did. They made a deal, and Oppenheimer agreed to then start a design laboratory. And of course, you know the story of the creation of Los Alamos that went on with it. And then when, when Los Alamos is starting, and in the very beginning, Oppenheimer does bring a lot of physicists from the RAD lab, the people he had been working with at Berkeley, Bob Serber being one, Louis Alvarez, many others, even Edward McMillan will come down for a while. But that's the core, but he needs to get a greater concentration. And he's, of course, recruiting some of the finest physicists in the world to work at Los Alamos. Always doing that. One at the top of his list was Enrico Fermi, to get Fermi to come and work at Los Alamos. And Fermi says, I'd be happy to come, but you should bring, he had a friend of his called Edward Teller, and who is a Hungarian-born physicist. And Jackie, you need to stop me if I get to 10 minutes. But
we're at 10 minutes, but go ahead and see if you can wrap up.
Okay. He brings Teller, and with that, Fermi had an idea of then using an atomic bomb to then make fusion reactions to make what later on we call a thermonuclear weapon. That process during the war did not go very far, but after the war, it picked up speed. Lawrence became very much involved with that thermonuclear research and he built a tritium plant to create tritium. And the Pentagon gave him some federal land at the Livermore Naval Air Station. And so that's where they moved and made this accelerator. And so coming out of the Manhattan Project after the war, when the Russians then became a nuclear power, then thermonuclear research took on a much greater importance. And eventually a commissioner from the Atomic Energy Commission asked Lawrence to create yet another design laboratory, this one to concentrate more on thermonuclear research. And that would then be the creation of the Livermore Laboratory and the rest of that story. Okay, it looks like I'm out of time, so I'll stop right there.
Great. Well, what an interesting history there. And it sounds like we may have an opportunity here for some of our historians to get together after this webinar and compare some of their notes and stories as to how this all transpired. I see that Rebecca has been able to come back online. Hopefully your audio is working and we can hear
Yes, I
about Sandia's
apologize.
role. No problem. Understand completely.
Okay, all right. Oh, we got slides. All right. Thank you very much for this opportunity. I apologize. I froze up just as I was supposed to go on earlier. I guess it was nerves. But I thank you very much for your time and attention today and this opportunity. I'm going to be talking about the other end of the Manhattan Project as the war ends and nuclear weapon work moves into the peace. I'm the senior historian at Sandia National Labs. Sandia is the piece of the nuclear security enterprise responsible for ordnance engineering, which is doing all of the design, testing, and specifying production for the non-nuclear portion of a nuclear weapon. It's a system integrator, making sure all of the puzzle pieces fit together into a working weapon. From a design standpoint, it basically turns the big boom provided by Los Alamos or Livermore into something the military can deliver. Sandia is a spinoff of Los Alamos. It is early among the pieces assigned to Los Alamos to move out of the lab and to its own site. As the nuclear weapons complex grew in the years after World War II, many of the functions that started at Los Alamos would end up at separate sites and institutions. Pit production went to Rocky Flats for a few decades, for example. And Sandia started as Z Division of Los Alamos in July of 1945 while gearing up for and fielding the Trinity test. Robert Oppenheimer reorganized some of Los Alamos. Those of you who work at big institutions know we have to reorg regularly. Keep swimming forward, I guess. It was part of Oppenheimer's and Groves's effort. The creation of Z Division was part of the effort to prepare for the stable continuation of weapons development and production in the post-war period, essentially looking out past the wartime effort and seeing how they can allow some things to grow and put things on a more stable footing. They gathered up the ordnance engineering elements at Los Alamos into one group, and they were trying to improve and expand those functions. Then they were also looking to move an element of the Los Alamos work off the hill. They couldn't expand a function up there at the time. It was crowded and there was a lack of utilities. Asked later, both Oppenheimer and Groves stressed that there was no room to grow anything up there at Los Alamos at the time. Now, Z Division included 4 elements. There's design, which is experimental systems engineering, electrical, mechanical engineering for production, and electrical engineering. And at the time, they were specifically going to look at new designs or improvements of the Fat Man type implosion weapon to include weapon safety, which is part of Sandia's assignment ever since. And the people brought into that piece of this were from E Division, from the ordnance engineering piece. The second element was field test, which is environmental and developmental testing, as well as supportive nuclear testing. Assembly, so assembly for use and for testing, putting them together, putting the weapons together. In the larger vision, this was to include an assembly factory, a real production type and capability, as well as procurement for the non-nuclear portion of the nuclear weapons. And fourth was military liaison, working with the military to ensure deliverable, usable weapons, right? The handoff, you have a smooth handoff. So it's an engineering group, as Bob Franklin pointed out, a whole lot of engineering going on in the Manhattan Project efforts and in the nuclear weapons complex since. I heard a talk decades ago by a grad student who was talking about how World War II is always referred to as a physicist war, and that's largely because not because anybody should shun the physics, of course, or snub at it, but because the hand-waving portion of the explanations of what the physicists did during the war were unclassified, whereas the chemists and the engineers' work remained behind the fence. And so we talk about it as physics, but there's a ton of engineering involved, ton of engineering going on up at Los Alamos during the war. So once they've established this group, Z Division, they need a place to put it. Again, they're going to take it off the hill. Functions need to be near an airfield to support testing, drop testing in particular. Ideally, it'd be relatively close to Los Alamos, to the mothership, right? And those functions included working closely with the military, so it'd be nice to be close to the military. So on the left here, you see the photo of the site selection photo from the site that was in the end chosen. Other sites were considered. I'm not going to talk about them. And we're looking, basically, we're hovering in the air west of where the current Albuquerque airport is, if you've been here. Come again, especially during Balloon Fiesta, spend some money. We're always happy. We're looking out west towards Tijeras Canyon. And this road that you can see cutting across the top left-hand corner of the photo is Route 66, Central Avenue. We're about a decade out from the Interstate Highway Act, so there's no interstate here yet, but there will be. And then in the military had 2 installations here in this location in the by mid 1940s. And Albuquerque itself has not grown out this far yet. Okay, Albuquerque is way off to the bottom left of this picture. Since then, of course, Albuquerque's grown out and basically reaches around and hugs the entire military base out here. But the military had acquired land out here on the East Mesa in January of 1941 to establish a training facility for bomber pilots, and that became Kirtland Army Airfield, which is the installation you see in the front portion of the photo. You can see their runways there to the right. They share runways now with the Albuquerque Airport, the Sunport. And then they also created a training center for aircraft mechanics and air depot personnel on an area in the back here, or in the top. You see in the top portion of the photo where the big white X is. Those are the runways from an airfield that was put in here in the 1920s, Oxnard Field. And then the military installation just to the left there, you can see the buildings there. And that became a convalescent center in mid-44, and it was known as Albuquerque Army Airfield. So this was an established defense space by mid-45. Part of it was selected for Z Division. And on July 21st of 1945, so the week after Trinity, the jurisdiction was transferred over to the Corps of Engineers to be part of the Manhattan endeavor. And that was this piece in the back, okay, where the white X is. And that's where Sandia, New Mexico is now. Many more facilities out there, of course. And after that, it was referred to as Sandia Base. And that all happened in July of 1945 because, nobody at Los Alamos had anything else to do. And Z Division was placed under the charge of Gerald Zacharias, who you see in the bottom right here. Zacharias had worked at radar at MIT during the war and then joined Los Alamos in 45. Headed up Z Division for a few months and then left and went back to MIT. Z Division itself began moving down to this new site in September of 1945, bringing down mainly the field testing group and some assembly. And people for the new division were drawn from Los Alamos's Ordnance Division, which I mentioned earlier, the E group, and they were the engineering group within the Ordnance Engineering Division. They were largely engineers. And they also brought the assembly group into Z Division. And this is some of the folks from the assembly group there at Trinity. getting ready to hoist the gadget to the up on the tower. And I'll just point out that up here we see Art Machen, Bill Stewart, and Herb Blair. Machen's going to come down and head some groups up at Sandia. And then down here on the ground, we see Phil Daly here in the funky hat, and then of course Norris Bradbury. So he's going to be briefly part of Z Division. All right. And this is what their initial organization. This is the org chart, such as it was from October of 1945. Would the world have stayed this simple? Okay, that you have ordnance engineering under Roger Warner. And he's heading it up because Zacharias has already left. And then experimental systems, Bradbury's here, but he's just going to be here for a few minutes because he's going to take over for Oppenheimer, of course, in October of 45. So we have experimental, we have the assembly factory, firing circuits, mechanical engineering, electronic engineering. All right, so that's what it looked like then. And this is what it looked like physically in February of 1946. We're looking into what becomes Sandia's main Tech Area 1 here, and you can see there's some construction going on. This was the first building built specifically for Z Division. This is building 828. It was a mechanical test facility, and you can see the completed building in the top right here. It's over here next to the base chapel, which was later moved elsewhere on the base to get out of the way of some of the construction here. Also, they were handling large amounts of high explosives in this mechanical test facility here. Seems to me you might want to keep the chapel there, but just for that purpose. But anyway, they moved elsewhere. And then parts and supplies ordered during the war for weapons for Los Alamos were redirected to Z Division. And you see the crates out here in the rows. Everybody used to joke that this was the stockpile in 1946. There was no stockpile in 1946. But anyway, and you can see we occasionally do get water here sometimes. But during this period, they're having trouble getting and keeping people and having trouble with enough space. They were bringing in buildings from other decommissioned sites as the war wound down, other military installations, bringing them in as well as doing construction here. And there's Roger Warner, who's going to head up Z Division for a little while. Huge turnover in these early months. And then as everything was trying to build up this new site, Z Division personnel, all of the assembly group was called to the Pacific to support Operation Crossroads, Joint Task Force 1, first post-war nuclear test. And the assembly group went out. Sandia is involved in all nuclear testing after this, of course, but Los Alamos learned of Operation Crossroads, the plans in December of 45. The test actually occurred in, there were 2 shots. These are weapon effects tests. There was an Able airdrop at the end of June, and then the Baker underwater shot that you see in the top left there, the mushroom cloud before coming up out of the water in July. So this is part of the group that went to the Pacific. There's Roger Warner again, looking a little more casual than he did in the other shot, and Phil Daly and Art Machen here, and Glenn Fowler. And they're all going to stick on with Sandia for quite some time. Art Machen, who was in the Crossroads photo, headed up military liaison at Z Division. And then at Sandia, when it became Sandia. We saw Phil Daly there. He was heavily involved in weapon assembly in the production arena at Sandia. And then Glenn Fowler, who we saw there in the middle, was part of the site selection group for the Z Division site, and then stayed on. He became director of field tests and then vice president of research in the following years. He was a legend out here for decades, heavily involved in forming up the lab in the 1950s and 60s. He even pushed for the addition of fundamental research to the lab. He was part of that movement in the late 1950s, which established basic research here at the lab. And then this is Operation Sandstone. This is the assembly group headed up here. See, they all have their shirts on. They look very tidy. So somebody told them they were going to have the picture taken. But this is our Machen's assembly group here at the site. They look very serious. And by sandstone, you do feel, in addition to the fact that they're all coordinated here for this photo, it does feel like things are running more smoothly, that Z Division's on a more even keel, and it's functioning with management in place with less turnover, and the activities well defined. And the nuclear weapons complex as a whole is standing up. We're seeing traction in production and expansion of the stockpile from this point on, really. Production had been increasing by 1948, sort of realizing the notion of a stockpile, that maybe we will have a stockpile. And the introduction of the Mark IV bomb and its production were a turning point. No more handcrafted weapons. Okay. And then in 1948, the assembly buildings opened to the south of Sandia's main tech area. Phil Daly, who I mentioned, ended up out in this arena running weapons assembly activities. And this was weapons assembly for storing weapons, not for testing, which we saw in the Trinity test. Weapons assembly had been going on in a military building on the base, but now Z Division has its own facilities here by late 48. These were a series of assembly rooms. You know, the parts would come in at the low end of the building and move on through a series of bays that were separated by rooms full of rubble that could collapse in case of an accidental detonation. It would have only been accidental. Nobody would have detonated on purpose here. And assembly at this point meant putting together all of the non-nuclear portions, including the high explosives. The pit or core was stored separately to be inserted into the rest of the assembly at the time of use. Even as these buildings opened, though, here in 1948, the Atomic Energy Commission already knows it's going to open Burlington as an assembly site, and then adds Pantex shortly after that. So Sandia, briefly, as Z Division, is in the weapons assembly business. It's the primary site for weapons assembly from 1948 to 1952, but that's it. It's
Rebecca, this
and then it
is
gets out of the
Tina.
business.
We have
Oh,
5
sorry.
minutes. Oh, no, you're good. We have about 5 minutes, so we needed to just wrap up and get that to.
Okay, well, let me just say that Sandia turns over, becomes an independent entity from Los Alamos in 1949. So I'll end it there. I apologize for going over.
No, it's okay. You're great. Thank you.
Thank you, Rebecca. What a great story. And for those who are still online, there's some phenomenal timeline histories at the Sandia website. You can pick those up on the INMM history website. And there's also a number of videos and oral histories that are available through Sandia about their efforts to build the stockpile. Last but not least, we have Alan Carr from Los Alamos, and I've challenged Alan with a very difficult task, and that is, after listening to all of this, the rest of the story here, to give us some of his perspectives in the context of the Oppenheimer movie and the history that Los Alamos also has on their websites. Alan?
Hey, thanks, Jack. And so my goal is I'm going to try and finish before we see Jack live again. What do you think? If you think it's possible, let me know in chat, and we'll see what we can do. So, yeah, I get to close this out today. And just when we think about the Manhattan Project, a huge national project, it employed 130,000 people simultaneously, just about in the summer of 1945. At one point or another during its existence, it employed about 500,000 people. So those two very different numbers tell you a little bit about the turnover of the Manhattan Project. Of course, the unsung heroes of the project, the construction workers. Construction was the most common job on the Manhattan Project. There would have been no Manhattan Project if there had not been people building all the sites that you've learned about from my colleagues today. And so, yeah, the Manhattan Project, really, really an incredible project. So everybody knows about Los Alamos. You got everything that you need in the movie there. If it's not on the movie, you can probably find it on the Wikipedia, right? So I thought, to close us out today, what we would do is I have picked my top five discrepancies between the reality at Los Alamos during the war and what was presented in the movie, because we've not got very much movie chat today anyway, and everybody likes a good list, right? So why not? And so reason number one, or I should say discrepancy number one, is I think that the laboratory was larger and more diverse than it was portrayed in the movie. The laboratory today employs 16,000, 17,000 people. Back during World War II, the technical staff was about 1,700. There were multiple divisions, all types of activities going on. About 11% of the workforce was comprised of women doing various jobs. A few of them, a very small number, were scientists. Some were technicians, some were computers, some were secretaries. But anyway, quite a few women there. And of course, there were a lot of people from the surrounding area who made important contributions at the laboratory, mostly as laborers to build the laboratory in the first place. But anyway, you didn't, I didn't anyway. I don't know how you felt, but I really didn't get that sense in the movie myself. And of course, although the movie was shot in New Mexico, Los Alamos was in a different area, but at least they got the state right. And I thought that it was pretty remarkable, the cinematography there in the film. So that is number one. And so discrepancy number two, you kind of got a little bit of a flavor of this in the movie, but there was a pretty significant weapons design conference in the summer of 1944. Originally, the laboratory attempted to build 2 gun-type nuclear weapons. The main one was going to use plutonium. It was called Thin Man. And Emilio Segre, Edward McMillan, and others, as plutonium became more available to work with experimentally, discovered that it would not be suitable for a gun. And that was a huge deal, because if you're going to build an enriched uranium weapon, you might have enough material for one during the summer of 1945, as it turns out they did. But if you wanted a novel new capability that could be reproduced rapidly, you really needed to make a plutonium bomb. So Oppenheimer reorganized the entire laboratory to do that. He ruffled a lot of feathers in doing so. But really, I think, to me at least, as the historian of the laboratory looking back at the war, that was a crucial moment in Oppenheimer's career as the director, making those tough decisions. And of course, they were successful. So reason, or I should say, well, I don't know why I'm saying reason, but anyway, discrepancy number 3 is the H-bomb story. I was kind of hoping that Tom would get into this too, because he has a lot of great thoughts on the early H-bomb program. When you watch the movie, you see Teller bringing up the possibility of a hydrogen bomb a little bit. It's kind of casually dismissed. The reality is that from day one of the laboratory's existence, thermonuclear work was conducted, and not just by Edward, but Edward and his team. And so I would say that as we look at the documentation from the war, Oppenheimer supported H-bomb development as much as he could without compromising the main line of research. This is something that Oppenheimer was very interested in, going all the way back to the Berkeley Conference of summer 1942. He was a proponent of this during World War II as the director, and Edward was not working in a vacuum. He had a lot of really good people working with him, and I'm working on a book chapter right now on that if you want to learn more about it a little bit later. So we are up to discrepancy number 4, and this ties in a little bit with what Rebecca was saying. In the movie, we see the military show up with a couple of trucks and a couple of boxes, pick up the bombs. I guess it doesn't show all this, but put the bombs completed in a couple of crates, and they tell Oppenheimer, hey, we'll take it from here. No, you won't. The military is not going to do anything by itself, because the military and the scientists of the Manhattan Project, the engineers, the technicians, it was a partnership. And so, there were probably 2 or 3 dozen people from Los Alamos on Tinian who put the bombs together, who ensured that they would work, who were there, who flew the mission. Harold Agnew, our 3rd director, was part of that team, the Project Alberta team, as it was known. He flew the mission. The little boy was armed in flight by one of our 2 associate directors, Captain William S. D. Parsons. And so, yeah, there's no military delivery without Los Alamos, and there's no delivery without the military. It's very much a partnership. It simply wasn't, the military shows up one day and Oppenheimer becomes irrelevant all of a sudden. So that's not really the reality. And finally, discrepancy number 5, at least according to me, and do remember, it's just a movie. I'm not picking on the movie. Remember, movie people try to, when they're taking on historical topics, they're trying to make something that is entertaining, perhaps at the expense of a little bit of accuracy, as to where historians, we're trying to make something really accurate, although it may bore you. So we kind of have different goals when you think about it. But anyway, I would like to point out, at the end of the film, major spoiler here, the world's not on fire. Oppenheimer did not feel like he had destroyed the world or wasn't scared of it. I think that, if anything, Oppenheimer was hopeful. Having been heavily influenced by Niels Bohr, I think that Oppenheimer really hoped that these new weapons would help prevent major conflicts between the global powers. And that's what's happened thus far. And I think that the complex of which you're a part of, which we're all a part of, is a major reason why. We are very much a part of J. Robert Oppenheimer's legacy and the legacy of the Manhattan Project as a whole. And do remember, I gave those numbers early on to show you just how much bigger than Los Alamos it actually was. I'm proud to be a part of the complex and proud to work at Los Alamos and to carry on this important mission. And so instead of dread, I do think that Oppenheimer, who never regretted the use of atomic bombs, although I never think he felt warm and fuzzy about it either, I think that hope is the word that I would use to describe him. And I would have liked to see that a bit more at the end of the movie. And so anyway, I've not seen Jack live yet. So apparently I've accomplished my goal, got done on time, and I hope that was worthy of the mission that I was given, Jack. Thank you for the invitation, and everyone else at INMM as well.
What a great wrap up, Alan. We really appreciate that perspective. The question I had was, were the fish bowls with the marbles reality? Was that something that was added?
I think it was something added, but you know, it was. I thought it was a great tool to bring people who are in the public not familiar with this history to help them to understand that going back to Hanford and Oak Ridge, the story of the Manhattan Project is very much the story of having the material available to make an atomic bomb. So,
right. Well, I really appreciate everybody's participation today. As you all can see, we could have made this an 8-hour session and probably still run over at the end. But a lot of history is out there in terms of oral histories. A lot of the folks that you see here today are helping to assemble that at the various locations. And we have other locations like Argonne, other of the science laboratories, where some of the work was also done on the Manhattan Project that have to be acknowledged as well. We're going to try to capture as much of that as we can on the INMM history website for students in particular who want to do the research into the history and understand how all of this came together. There are many, many books, and we're going to, as we put this webinar together, we realized one of the things we were missing on our INMM history website is a bibliography of books that have been written. Of course, American Prometheus is the one that the movie Oppenheimer was based on, and that will be on our list in the future, as well as many others. So thank you all. And Tina, would you like to wrap this up for us?
Like I said at the beginning, this is just the beginning. So we'll continue these webinars, and we're just so excited for the support we receive from you, from all of the speakers. And thank you again. Please go to inmm.org if you're interested in becoming a member, and please join our social media channels if you're interested in hearing more about these upcoming events as well. Thank you.
Thanks, everybody. Mark, any final words for us?
No, what can you say, right? This was fascinating, interesting. I'm going to probably watch the recording again to refresh my memory on some of these gems. And I'll leave it at that. And really, everyone who attended and whatever we might be able to do in the future to attract your attention and educate the public as well as ourselves, we are game for that. And if you have suggestions on topics you'd like to hear in the future, please don't hesitate to let us know. Thank you.
Bye, everybody.